Let's begin. So today we'd like to turn our attention to section 5.2. And number 87 is a good example of this that we were just looking at in the homework. I actually didn't realize I'd put one of those in there that asks you to prove all the problems tonight. I shouldn't say all. I think most of it, at least. The problems tonight will ask you to prove such and such. We'll ask you to prove a statement. So we want to look at different techniques for how to prove. I'm going to give you a couple tips for how to prove an identity, and then we'll do a couple of examples in a second. So these are modified from your book just slightly. So these appear in your book, I think, as well. I don't know if you want to write them down, you're welcome to. Let me go through and talk about why each one makes sense to me, though. So by prove a statement, I mean something like this, right? So here's, for example, all right, thanks, guys. So for example, someone might say, prove 1 plus tan squared x over cosecant squared x is equal to tan squared x, right? And the proof of this is written on the board. It's number 13 over there. Okay? So in some senses, in particular problems that you'll be doing tonight in homework 2, it's actually easier than last night because we're basically just saying simplify, and we've given you the answer, right? Yeah. So the proof for this is C number 13. It's over there on the board that Rosie, you did that, right? So Rosie, in fact, even though the instructions for that problem were simplified, she's actually constructed a proof of the following statement, that for all x, 1 plus tan squared of x over cosecant squared of x equals tan squared of x. Now, it's also possible that her work that's shown on the board could be run in reverse. We could prove that tan squared x is equal to the first thing, right? But if there is a more complicated side, then I think that we're all smart to start with that side. So that's what the first tip says. If there is a more complicated side, then start working with it and simplify it, do whatever you can to it. If necessary, I bailed out on this red problem here. If necessary, convert to sines and cosines if you feel like you're getting a little intimidated by all the cosecants or whatever, okay? And then a lot of times what you have to deal with is just like algebra. You remember the warm-up from yesterday. It just reduces to maybe a problem with some like A's and B's, basically. We have sine and cosine. And maybe we can just play around with the algebra a little bit. Your algebra game has to be strong though here, right? Hopefully you're fine with fractions within fractions and clearing denominators and add all those kinds of things. Combined fractions. You saw on the warm-up how that was fruitful, right? There wasn't much to do on the warm-up except to find a common denominator, and once you did, then the rest kind of happened for you. This one's not been super obvious to us yet, maybe, using the difference of squares, this little identity that we know because of algebra, to set up different instances of the Pythagorean identities that we saw yesterday, those 3 identities. You'll see why that's useful before the lesson is up today. Keep the target expression in mind. This didn't come up here in the example I just chose. But you can imagine, in some of the examples we'll do, where we have one expression that's complicated equals another expression that might be complicated. And simplifying one of them is not necessarily what's going to happen. It's really directing the course of one expression and so that it comes out to be the other expression, right? So whatever that might mean, we might introduce things, we might make things intentionally more complicated along the way, not simplify, whatever, in the name of getting to that other expression, right? So just keep that in mind. And if absolutely necessary, then we might work on both sides as well. And I'll say what I mean by that in a minute. I don't mean what you think I mean. Okay. All right, so again, these will all be made clear as we do a couple examples. See, these are my tips for proving identities. By the way, I should ask right now because this will be kind of maybe an indication of how tonight's homework will go too. Thumbs up, thumbs down on the homework last night. How did you feel? And I shouldn't say how you feel. How did you do? Whether it was difficult or hard? Did you like it? How did you like it?
I liked it.
All right, because I know it's difficult. Some of it takes a little bit of while to get, but but especially tonight too. I think you'll find. All right, thanks. All right, it was my fault. That was my fault. All right. The homework tonight will have the same kind of flavor in the following sense. I think a lot of these problems feel like puzzles. And so for you, if you're a student who is like looking hungry for a formula, then these might frustrate you, right? Because like there's no right way to do one of these problems. But if you like a good puzzle, what I certainly do, then these are fun, right? So I would encourage you to, and that's what I said, do these problems with an eraser nearby, right? Try stuff. If it doesn't work, it's like, okay, whatever. It's like not the end of the world. I'll try something else. And eventually you'll unlock the problem. And that's how this feels when you get these. It's like, eureka, yeah, I got it. Feels good. All right, so let's try proving one that's not quite as obvious about the simplification. We want to start with the more complicated side if there is one. And the temptation, this I want to kind of head off right at the pass. We'll say this again and again, and I know that a lot of you will do this, even though I'm going to kind of warn you against it. Do not multiply both sides of this equation by something. Right? This is something we're going to prove true, but right now it has not yet been established true. So I know there's like a strong temptation when you see an expression that has all these fractions, you want to like, oh, let's multiply both sides by sine theta, or let's multiply both sides by 1 minus sine squared of theta, or something like that, right, to clear fractions. But you may not do that, because this has not yet been established as a true statement, right? And the property you're trying to use is a property of equations, and this isn't necessarily an equation yet, right? So the way we have to prove this is by a chain of equalities that shows one side equal to the other side, okay? So I'm going to start with the left-hand side. That's what LHS means. And I'm gonna forget about the right-hand side for now. Eventually I do want to think about it, but I'm just going to... You can start with the right-hand side if you want to.
I'm going to go with it.
All right, secant squared theta minus 1 turns out to be tan squared, right?
Because of the property.
That's one of the things that we should know from yesterday. Eventually that'll become second nature to you. Tan squared is sine squared over cosine. Like I said, you got to be comfortable with like fractions within fractions here. And then if you can see it right away, then maybe you can cancel things out. But we can write it this way too: sine squared theta over cosine theta times 1 over sine theta. Isn't that what it means to divide by sine, the same as multiplying by its reciprocal?
So you just get
So we get sine over
cosine.
Sorry, where'd the cosine squared go? Where is this?
Yeah, okay. It's not tangent. Confusing.
All right. And at this point, we're done. Oh, wait. Hold up. We got to go back and look at what we're trying to do, right? This is where this departs a little bit from what you were doing last night, which was just like straight up simplifying. Now we have to, again, that one of the bullet points said, keep the target expression in mind. So, what are we trying to do? Oh, right, we're supposed to make it this, but we're kind of done then, aren't we? What do you see? I mean, isn't this equal to that expression by one of the other Pythagorean identities? Okay. And then when we're done, we might write something like QED if you want to sound smart. Anyone know what that stands for? It's an acronym in Latin. Do you know? All right, listen. Alex, say it. Let's use your best Latin. Go. Yeah, very, very close. Samantha, you're excited about this. Go ahead. Yeah, that's right. That's right. Right. So, and what it means is quod erat demonstrandum, which was to be demonstrated, and the reason that grammatically makes sense at the end of this statement is the reason that if you read it, let's read it out loud. What have we just done? We've just said the left-hand side. Look, everybody. The left-hand side equals this, which 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 equals the right-hand side, which was to be demonstrated. Right. So that's the reason that makes sense. grammatically. Okay. A lot of times people end the proof with this black box.
Wait, are we actually gonna have to do full of like proofs?
I mean, this is a proof, yeah. So you can
But
end
we
it
have
with
to write like
if you want to
all the
sound smart.
properties and stuff right now.
Not necessarily. No. The black box in math is used as a symbol. It means QED, so it's just a convention that mathematicians use sometimes. So if you want to use that instead of QED, they mean the same thing. Or sometimes mathematicians use other things to make them sound smart too. Like they might write as desired at the end, right? This. Oh, that's. Right? The left-hand side equals this, which equals this, which equals this, etc., equals the right-hand side as desired, right? Or you could say, and the proof is complete or something. There are a couple different ways you can end it just to make yourself sound smart, okay? They're not required, but.
So, could you simplify both sides to like equal the same thing?
Yeah, so, right, and in fact, you're kind of maybe thinking about that as soon as you start the problem. So the proof we just did looks like this, doesn't it? We took A and we turned it into B. But the proof that Adele is suggesting is one that looks like this, right? We could can we manipulate A and manipulate B into two expressions that are equal? And that is sufficient too, yeah. The only thing we can't do, and I hope you understand, you can appreciate this is good, but I just want to make sure you understand that you can't work across the equals, right? So if you want to work on both sides, that's fine, but put each side in its own hermetically sealed box and work on it, right? What you may not do, though, is stuff like I said at the beginning, multiply both sides by 2 or whatever. You can't do that, okay? So both these ways are okay, and we might have to resort to that soon. All right, I want to give you some think time on this one, so I'll give you a 2-minute head start on this. All right, you guys have had a chance to look at it a little bit here.
Oh, that makes sense, yeah.
Yeah, so those who are still, I don't want to race into this, but hopefully you're getting a chance to do this yourself. There's no substitute for that feeling. It feels great, doesn't it? When you unlock it. It's a wonderful, great feeling. And you gotta be careful. It might turn you into a problem solver. Maybe it might even turn you into a mathematician. All right. So what'd you do? What's the next hint you might give someone here? What'd you see? Maybe turn this into sines and cosines or something?
Yeah, that's the easiest way to do it. And then I put it over 1. What? I put the sine square
Sine squared over 1?
over 1, and then I multiplied the cosine and by 1.
For those who still didn't get it, are you seeing where we're gonna go with this? Maybe I don't know.
Oh, I don't know what
I see. Even now, I'm thinking about the target expression and how I want to get it eventually to be looking like the right side. So, what did you do next that was helpful here? Maddie says factor out a sine squared. Do you like that idea? So inside the parentheses there we have sine squared theta. If we wanted, we could write that as a secant squared, I guess. Theta minus 1. Oh, which is tan.
Yeah.
Tan squared, yeah.
But then do you have to prove something on the right hand side?
No. I think we're done.
Oh, you don't have to do anything on the right hand side once you get the left?
No?
Oh.
I mean, the proof, if you happen to start with the right-hand side, the proof looks like this, right? right? It's the same proof if you start with the right-hand side, just going the other direction, right? Listen, please. Peter, go ahead.
You solve for like C
Okay, guys.
at this point. Do you just write the little box with the
If you solve for, say it again.
like I end up with tan squared theta equals tan squared theta. You just have to write the little box of the
Wait. There's no way that you could have ended with tan squared theta equals tan squared theta unless you divided by sine on both sides.
I added.
Or you added something. You added sine on both sides? Illegal. You can't. Okay, so you can't do that because the thing you started with is not necessarily proven true yet. It's called this is a logical fallacy called begging the question or assuming the consequence. Right? If someone says prove A, and you start by saying, well, let's assume A is true. Wait. Flag on the play right away. Right? Like you just assume the thing we're trying to prove if you're going to do that. Right? Like, what allows you to add sine on both sides? It's the assumption that these are equals. Well, that's the thing. That's the thing that we're trying to prove in the end. Does that make sense? Okay, I just want to make sure that we're clear on that. I know, like, I've harped on you a couple times on different assessments when you've done that too. I say, show this is equal to this on the log test or something. We had like said, show this expression equals this expression. That's how you have to do it. You can't start by assuming they're equal. Yeah.
But can you start from the conclusion and then prove that it's not true and then that proves the
Yeah, but that's not what he was doing though, right? Yeah. You could start with the conclusion and use the inverse of use the negation of the conclusion to prove the negation of the hypothesis. But that's a little bit far-fetched here. We can't really use that principle here. That's called the contrapositive that you read. All right. Let's try another one here. Yeah, this one especially, I don't know what to do here. I'm at a loss right away. I mean, it's already in terms of sine cosine. It's already, I mean, what do I do?
Hey, that's so cool.
That numerator, man, that kills me. That 1 minus cosine.
That makes it so easy. What? But then it becomes sin x over sin x.
I hear some mumbling about the fact that
Sin x. Dang.
the numerator on the left side is sine, right? But it's not. I mean, it's not a typo. You wish, don't you kind of wish it was 1 minus cosine squared? Yes. Hey, you know what, guys? If you want something in life,
Make it happen.
make it happen. How can you make that happen? How can you make that happen? I think I agree. I'd love a 1 minus cosine squared there. That'd be very cool. That's true. Make it happen.
So what do you do? Can you show us before the class runs out?
Oh, yeah.
What do you do? That's what I thought.
One minus
Oh, you.
squared, yeah.
Oh, just to get square.
1 minus cosine. Well, I don't know.
Wait, but then do you have to multiply the other side? No, but you can put the reciprocal on the other side also.
That's true.
Tell me what I can and can't do. How do you? Oh, can you cross multiply it?
No, because you don't don't know that this is true yet.
What do you do? Can you show us before class is over?
All right. I'm ready to hear the big key that unlocks it. Maybe I'm starting. Are you starting on the left-hand side? Maybe again. I don't know. It actually is equally difficult on either side. You can do either one. But all right. So I hear you say I'd love a 1 minus cosine squared instead of a 1 minus cosine. So how did you make that happen? Those who were having success with this, what'd you do, Noah?
Yeah, multiply by 1 plus cosine.
All right, so, and I think, like, that's, like, the big power play here, isn't it? In fact, once you realize that that's what needs to be done, it's like, I think you can see it all the way to the end, maybe, can't you? Like, you can't even write as fast as you can think about how excited you are about what's going to happen here. Do you see it happening already? On top, we get 1 minus cosine squared, is what we said we would get.
What equals sine x?
And on the bottom, we have sine
Sine x squared, I know.
times 1 plus cosine. The reason I'm excited about this is because I have the form of the target expression in mind. And this 1 plus cosine not only solves my problem, I want a 1 minus cosine squared maybe, but it also introduces one in the bottom, which is not a problem. It's actually what I want in the end, right? So like, there's a lot going for me here. This is up top sine squared. It's like the whole reason I did that. You see how that one move is kind of like the big giveaway?
It's like chess.
Do we have to test whether you're getting them to know?
Oh, okay, yeah, okay. I got you. That makes sense. That makes so much sense.
All right. So if you follow that, the proof, like I said, the proof starting with the right-hand side. All right, guys. Sorry, my voice is hurting again here.
Yeah, it's hurting.
The proof starting with the right-hand side is almost identical. It just goes this way instead, right? Right-hand side equals this, right? Someone just asked an interesting question. Hey, guys. Thanks. Someone asked an interesting question. Will we ever ask you to prove something that's not true? I'd like to address that question right now.
Yes.
So, there's a nuanced answer to that. If we ever ask you the question, if any mathematician ever asks you the question, prove the following statement, period, in a math class, we will always give you a statement that is true, right? So that in the end, we're not like trolling you, okay? We will sometimes give you instead though the instruction prove or disprove the following statement. In which case we're asking you to both establish whether you think it's true or not, and then if it happens to be true, prove it to be true, right? So you understand the difference in instructions. So we actually have later we'll give you an assignment where we ask you to do some all of them are the title of the worksheet is prove or disprove. So we'll do some of those too. All right. I think this is an excellent place to kind of round it out. I think you're well equipped for homework number 2. Really, you just need to spend some time in the trenches, and in the end, like I said, in the end, I think you're going to find this fun, relaxing, therapeutic. You might want to make yourself a cup of tea, put on your slippers.